All right, so we are live. So I welcome everyone. I am Aishwarya from Chinta team, and today I have Siddhant Shah with us, and he worked on an interesting research project on hyperbolic geometry, and he is going to explain that in this live session. So yeah, Siddharth, handing it over to you.
Yeah, thank you. Hello, everyone. I'm Siddhant, and today in this video, I want to talk about some insights which I gained from my research project in exploring a non-conventional proof about Seven Circles Theorem in hyperbolic spaces. Next slide. Yeah, so to begin with my presentation, first I would like to discuss what Seven Circles Theorem basically is, which we have defined in the Euclidean space, which we have been studying in geometry since so many years. So let a naught, a1, a2, all the way till a5 be six consecutive points around the circumference of a circle O. Then if we draw circles which are internally tangent to an outer circle O at these 6 points, and they are also externally tangent to all these circles to each other in terms of pairs. That is, like for example, if we have a circle that is a1, then it has to be tangent to a2 and a3, a2 and a6, and I'm saying that wise. So then we're saying that the segments a0, a3, a1, a4, and a2, a5 concur. Can you move to the next slide? So this is the diagrammatic representation of it. Ma'am, can you move to the previous slide? Previous slide. So, like, to be more, in other words, like in simpler terms, I just want to say that if we draw an initial circle, like if we have an outer circle, and if we are arranging six circles, any circles which are tangent to each other and also to the outer circle, then we say that if we join any 3 points, if we draw any three line segments which are opposite connecting to each other, they always concur at a point. Yeah, next slide. So to like I initially started this project by exploring the proofs which were already existing. I did a literature review, and I found out that there was one proof which was quite prominent in the Euclidean geometry about the proof of Seven Circles Theorem. So it is something related to the Sievers theorem, where they have proposed one theorem based on which they have completed their entire proof. So the theorem states that let A1, A2, A3 all the way till A6 be six consecutive circles around the circumference of a circle. Then the chords A1, A4, A2, A5, A3, A6 concur if and only if A1, A2 times A2, A3, A4 times A5, A6 are equal to A2, A3, A4, A5 and A6, A1. So to like just show you the figure of it, which is in the next slide. So this is this figure which I'm talking about, and if you go to the next slide, I have shown a proof of it, which states that suppose that we have A1, A4, the line segments A1, A4, A2, A5, and A3, A6, and they are all meeting at one point as it was present in the previous figure. Then we see that in the previous figure there is a similarity of triangles which is visible, and whenever there is a similarity of triangles visible, we always get to the proportions of it. So I figured out that when we take the proportions of the line segments A1, A2 over A4, A5, that is equal to the A1, A2 times P. That is the line segment we are connecting to the center, and also A5P, which is again the line segment. And I translated this into other things also, like A5, A6, A4, A5. And likewise, I found that whenever we multiply all these equations together, that is 1, 2, 3, 4, we together prove the entire theorem which was present as it presented before. And it is known as the Sievers theorem for chords. So this was the first proof which I explored that was present in Euclidean geometry for the Seven Circles Theorem. Next slide. So moving on, now my idea for this project was to explore that Seven Circles Theorem also holds true in the hyperbolic space. So I wanted to explore that if it was true or not. In other words, I wanted to explore an analog. So what I did was initially I explored what hyperbolic geometry was, and I found out that hyperbolic geometry was discovered based on the Playfair's axiom. So the story behind it is something like that. When Euclid published his book Elements, which proposed a lot of Euclidean geometry, he proposed five axioms which were quite fundamental to prove each and every theorem which we study today in Euclidean geometry. And the fifth theorem, which is also like modified further to be the Playfair's axiom, states that if we have any line, like if we have any infinitely straight line, then there is only one and only one line which is parallel to it. And if we draw any other line, they're saying that they always intersect at a point. So but however, this was a quite controversial statement to say at that time. So a lot of people, lot of mathematicians has debated upon this, and they found out that it is actually not true in other metric spaces, and it led to the discovery of a completely new geometry, which is known as hyperbolic geometry. So in hyperbolic geometry, the proposition is something like this: that whenever we have any line segment, they're saying that there are infinitely many parallel lines that exist to that given line. Ma'am, next slide. So to present my idea, this is one of the models of the hyperbolic geometry, like where hyperbolic space is introduced, and it is known as the Klein model. We can see that if we have a line segment AB, which is actually a line because it is touching the unit circle. So here we are representing the unit circle as the complete boundary. It is the complete geodesic. And whenever we have a geodesic like A to B, we see that there are infinitely many parallel lines which we are able to introduce if we visualize it to that point. Moving on, uh, this is also another model which is proposed in the Poincaré, which is also known as Poincaré disk model, and it is very crucial to exploring the proof in our paper because we have transitioned from Klein model and Poincaré disk model, and we have together come up with a proof of it collectively. Ma'am, next slide. So, to before we explore our proof, I would like to discuss some prerequisites so that they are very helpful in exploring the proof and they help out in introducing the ideas which I have written. So, the first prerequisite which I would like to talk about are the geodesics of the Poincaré disk model. So, there's one lemma proposed based on it, which says that the complete geodesics of model are circular arcs orthogonal to the unit circle. So, if you go in the previous slide, ma'am, we can see that all these geodesics, which are the lines basically, they are all orthogonal to the unit circle and they are all touching the unit circle. So in this, we're saying that if it is touching the unit circle, then it is an infinitely straight line. And ma'am, next slide. Next. Next slide. Yeah, and in this figure, we can see that if you only want to draw one line segment, then it is a circular arc, which is actually in the solid lines. Ma'am, just a second, my screen froze. Hello.
Yeah, hello.
So,
I think my screen has frozen. I'll have to rejoin. Like I'm not. Just a second, ma'am.
Okay, sure. Okay, so while Siddhant is rejoining to explain his research project, I would like to inform that if anyone is having any questions regarding this project, you can comment it down here. It's a live session, so we can also clarify that from Siddhant itself. Mm, yeah, okay, he's here.
Yeah. So sorry. Actually, my screen froze in between.
No problem.
Yeah. So I was explaining that the geodesics, as I was mentioning. So there's this one line segment which I've represented, which is in the solid line. So we can see that it is a half circular arc, which we can see from the figure. So, ma'am, can you go back to the page? Yeah. So this lemma was basically proposed through a proof, and I would like to talk about that. So the proof basically states that whenever we have some angles in a Poincaré model, they are always preserved because of the inversion. So what we did here was explore the idea that whenever we have a Euclidean plane, we converted that Euclidean plane and we performed inversion to encircle it around the unit circle, so that we are defining a new boundary in a new metric space. So now in this geodesic, which is represented as h square comma d height, We're saying that all the line segments and all the lines are always orthogonal to the x-axis, as it was the case in the Euclidean geometry. Similarly, it is also orthogonal in uh, hyperbolic geometry. And whenever we also perform inversion, it is also known that it preserves distances and everything. So we can say that everything is preserved except the fact that we are just representing it in a new model. I'm next. Yeah. So based on this diagram, can you go to the previous slide? Yeah. So based on this, there's one remark which I discovered, that was that the diameter of the unit circle is a is the complete geodesic. So what they're saying is that a complete geodesic is when the magnitude of the line is infinity. So the magnitude of the line segment is infinity. All these lines are known as a complete geodesic. Yeah. So moving on, I would also like to discuss one more lemma, which is important to be introduced in hyperbolic geometry. That is that of an ideal triangles. So triangles looks like a little bit different in hyperbolic space. That is that whenever we have three ideal points, that is 3 points that are at infinity, then the triangle looks something like which is shown in the next slide. Um, So we can see that the ideal triangle has 3 points which are touching at infinity. So it is known as an ideal triangle. Now there is also one more thing which is known as a semi-ideal triangle, where there are 2 points which are touching the infinity or the boundary, which are present at the unit circle, and there is one point which is inside the complete inside the space. And there's we also have one non-ideal triangle which has all the points basically inside the hyperbolic space or inside the unit circle. So based on this, we explored the remark that like similar to an ideal triangle, an n-sided polygon in this hyperbolic space also has a lot of ideal points, also contains ideal points. So it was very important. This was one point which was very important to us in exploring when we were drawing hexagons in proving in proving seven circles theorem. Ma'am, next slide. So the second prerequisite which I would like to talk about, which is very important, is that of a horospheres. So the notion of horospheres is that whenever we have a hyperbolic disk that is gamma one with the center ZO and the radius r in the hyperbolic plane, we see that when the z naught converges to x-axis, that whenever it is approaching x-axis, the circular disk becomes asymptotically tangent to the x-axis. So at that time we see that they have infinite magnitude, and the circumference of this entire circle is known as a horosphere. I have in fact also diagrammatically represented it in the next slide. So this is what I'm talking about, that whenever we have a hyperbolic disk and whenever there is a point which is approaching the x-axis, we see that the circumference is becoming like that. To the previous slide. So the proof of this was basically extended from the Poincaré disk model itself. And yeah, from that, this was the concept which was very crucial in this. Next slide. And the last prerequisite, which I would like to talk about, was that of an alternating perimeter. Now, alternating perimeter is that whenever we have an hyperbolic polygon that is n-sided in a closed loop made by connected by infinitely many hyperbolic geodesic segments, at that time we define the alternating perimeter as next slide. That like for example, if we have an even-sided hyperbolic polygon with sides s1 s2 all the way till s10 s2n, the lengths of its so the alternating perimeter is defined as the alternating sum of all its lengths. So the formula for calculating it is that we calculate s1 plus s3 plus s5 all the way till all the odd line segments, and then we subtract it from the even line segments. That is known as the alternating perimeter. I've also generalized it below for reference. Can you go to the next slide? Yeah. So now, as we have covered all the prerequisites, now I can easily discuss my proof to actually show you how I proved the seven circles theorem. So first of all, I proposed a lemma that was that alternating perimeter of an ideal hexagon is equal in magnitude to that of a non-ideal hexagon. So this, I proved it by defining that if we have some sort of line segment, uh, LK, for example, LK tilde, as the finite length of the edge between the borders of the disk, if we change the radius of the disk, we add and subtract the same amount from the alternating perimeter. Therefore we introduce the idea that alternating perimeter is always independent of the radius of the horospheres. So when the radius of the disk, for example, is 0, we say that the alternating perimeter becomes L1 tilde minus L2 tilde plus L3 tilde minus L4, and so on. It becomes an alternating series of things. Moving on. And based on this, we proposed a proof that about the Seven Circles Theorem, that we represent the hexagon, for example, A naught, A1, A2, A3, all the way till A5 in a Klein model. And we observe that the straight lines A naught 3, A naught A3, A1 A4, and A2 A5 in the Klein model are complete geodesics in it. Now, we convert that into a Poincaré disk model, and thus we have to essentially prove that the complete geodesics, that is A1, A0, A3, A1, A4, and A2, A5, concur in a Poincaré disk model. So this was the whole idea, that we first introduce the Klein model, we draw an hexagon in it, and then we convert that into a Poincaré disk model, and then we go back to the Klein model again. So this is some sort of a diagrammatic representation which I've shown, that we are transitioning from the Klein model to a Poincaré model, and we see that the hexagon is becoming something like this, which is shown as a figure. Yeah. So the technique we utilized to prove this and to introduce this idea was that if we consider gamma 1 and gamma 2 to be two circles tangent to each other at R, in a hyperbolic space at P and Q respectively, that the geodesic from P to Q, denoted as PQ, must also pass through R. So I've represented in the next slide. It states that this is the representation of it, where we can see that it is always passing through that. So like we prove this so we have introduced a proof of it ahead, but before that I would like to say that this was one of the lemmas which I discussed, and it was crucial in proving the fact that there will be no portion of geodesics in the ideal hexagon outside of the horosphere. So what we have done is that whenever we introduce the hexagon in the Poincaré disk model, we introduce many horospheres which were connecting to it, and whenever we increase the radius of it, we saw that there was no space in between there was no space in between, and at last the alternating perimeter of the thing was becoming 0. Now moving on to prove the lemma 3, which we already discussed. We did it something like this, that we introduced gamma 1 and gamma 2 to be two circles tangent to each other at R. Then we saw that if we let L be a point of intersection between the lines tangent at P and Q to gamma 1 and 2, since the geodesics are always orthogonal in Poincaré disk, the tangents P and Q must pass through the center of the geodesic arc PQ. Hence, the center of the geodesic arc is L. Then, if we are able to see this, then we see that the line segments LP and LQ are actually the radius of the geodesic PQ. And furthermore, I also said that the pairwise radical axis of three non-concentric circles, which were visible in the previous slide, are concurrent, which is actually known as the radical axis theorem. And the radical axis between gamma 1 and gamma 2 must pass through L, which is the radical center. Thus, LR, which is the line segment which you described, is tangent to gamma 1 and gamma 2 always, implying that LP is equal to LR is equal to LQ. And so, point R lies on the geodesic PQ. Can you go back to the previous slide? So here is the representation again of it. You can see that the lines are equal, and the point R is becoming a geodesic inside it. Yeah. Next slide. So now moving on, as I introduced the idea before, that we are going to introduce horospheres inside the Poincaré disk model of this hexagon, and we are gradually increasing the radius of of the horosphere, and we are seeing that the point r actually becomes like the magnitude of the point r actually becomes zero as they are becoming tangent to each other. So as a result of this, we explored that the alternating perimeter which we wanted to calculate, that was labeled in the blue lines before in the initial scenario, we're seeing that it is gradually becoming zero. Next slide. Yeah. And based on this, we saw that that after that, if we connect the opposite vertices of the triangle in that case scenario, we see that there are a lot of segments which are being built up in between. And our aim is to prove that the area which is highlighted below is zero actually, so that we are able to prove that they are actually concurring at the point. Next slide. So based on this, we actually introduced another lemma, which was that for any ideal hexagon P, ideal hexagon is when all the points are touching the boundary, that is the unit circle. The alternating perimeter's magnitude is always two times the perimeter of the each and every triangle which we are introduced before. Next slide now. So after we combined a lemma 4 and lemma 5, we actually were able to build a new lemma, which actually was important in proving the Seven Circles Theorem in hyperbolic space. That was that we have P as an ideal hexagon, and suppose there are horodisks H1 all the way till H6 placed at the ideal vertices of the of P in such a way that every two consecutive horodisks are tangent to each other. That is, the alternating perimeter is becoming zero as we are increasing the radius. Then the hyperbolic geodesics connecting opposite vertices of the P concur at a point always. I have represented in the next slide. So we found out after a lot of calculations that the area which I introduced in before was actually coming out to be zero after a lot of calculations, and thus we were able to prove that it was concurring at a point. Next slide. So based on this, we observed that the segments of the hexagon in the circle are actually cancelling out, and the alternating perimeter is becoming zero, and thus we are able to prove that the hyperbolic. We are able to propose a hyperbolic geometry proof of the Seven Circles theorem based on this. So more details about my paper can be found out in my publication in SSRN and JSR, uh, which is known as which I've titled as a proof of Seven Circles theorem using hyperbolic geometry.
Okay,
Yeah.
thank you so much for this lovely presentation, Siddhant. I hope it helped some of the kids here who are watching us live right now. And also, for I do not see any comments here, to ask you. So, if anyone is seeing the recorded version of it, if you have any questions, just put it down in the comment section, and Siddhant will be able to answer them. We will be in touch with them, and we will be able to get your answers. So Siddhant, thank you so much for joining, and also the audience who are with us in the call today. Hope you have the great rest of your day. Bye.
All right. Thank you.